let's continue with the class last time. So we did introduction of the plane stress. So why in real life situation for the 3D problem we can approximate as a 2D plane stress problem. Um, and for the derivation part, if we have a state stress of a 2D problem, we have three independent components. For all the others on the third direction equal to 0. So we have three independent components, stress components. And if we want to know that on a general angle theta after rotation for theta degree, what is the sigma x prime, sigma y prime, and tau x prime, y prime after this rotation of theta? We did a free body diagram. So let's say basically if you want to figure out on this plane, this inclined plane, and the definition is from positive x, the before rotation, the original global xyz coordinate, rotate to x prime, y prime, z prime, counterclockwise rotation, theta is defined counterclockwise, or we can say that if I take a inclined plane, this is also considered as theta. It's the same angle. And we did a free body diagram. So basically all the stress component on each surface and the area of each surface. Let's say, of course, if we define this inclined plane is delta A, then we know that the blue area should be delta A times cosine theta, and this green area should be delta A times sine theta. These are the surface, they are the stress applied on. And for the stress component on each surface, let's say on the blue surface, we have sigma x, tau x, y. On the green surface, we have, because it's y plane, we have sigma y, tau x, y. And on the red surface is, now this is the x prime coordinate after rotation, and this is the y prime coordinate after rotation. So we have sigma x prime, tau x prime, y prime. And stress times area equal to the force, right? So normal stress times area equal to normal force on the plane, and the shear stress times area equal to the shear stress on the plane. But what I'm saying that here is that if the stress on that area is uniform, but of course, since we are taking a very small cube or square for a structure on this very small area or cube for 3D, we can always assume that at that small area or that specific point, those stress components, they are uniform distributed. So now this is just put into one graph, like easy for us to do the equilibrium equation. So basically, all the force in the x prime direction, we have one equation. All the force in the y prime direction, we have one equation. And we have a expression of sigma x prime, which is the normal stress on the x prime plane. X prime is after rotation as a function of theta, and of course, sigma x, sigma y, tau x, y. And the same thing, the shear stress after rotation, we have function of theta, and also sigma x, sigma y, tau x, y. And we use this one to simplify our expression. And of course, this part is true. It's just pure math. It's not really content of mechanics materials. So this now we get this equation sigma x prime, and let's simplify this equation. Sigma x prime, we could write as half sigma x plus sigma y, and half sigma x minus sigma y cosine to theta. plus tau xy sine 2 theta. This one and this one, they're the same equation. I just like move these two term here and also two cosine theta term here, and last term keep the same. So now for the tau x prime y prime, we have half of sigma x minus sigma y sine 2 theta tau xy cosine 2 theta. So these are the two very important equations that we need to use for stress transformation. Basically, I can say that any plane, any angle rotation here, counterclockwise theta, I mean, this theta can be 30, can be 60, can be 90, can be any angle, as long as I know the angle, as long as I know the original sigma A, sigma X, sigma Y, tau XY in the original coordinate system, I know the stress on the plane that after rotation. And of course, this is only two of them. We need one more. So here is the sigma x prime and tau x prime y prime. We need sigma y prime. And of course, you can do a new set of equilibrium equation, free body diagram equilibrium equation to derive the sigma y prime. But this is an easy way, because for sigma y prime, if you check this original graph, this rotation theta, we get sigma x prime, right? And sigma y prime is here. So in the equation that we already derived for sigma x prime, if we replace the theta equal to theta plus 90 degree, we get expression for sigma y prime. There's no need to do a new set of free body diagram and equilibrium. Of course, you can do that. You get the same answer. It just takes more time. But an easy way is just understand in the way as that since we have theta defined as counterclockwise from the x to x prime, right? Counterclockwise theta, and this theta can be any angle. It can be any angle. So if I replace in the expression that we derive for sigma prime, we replace this theta equal to theta plus 90 degree. We get the normal stress on this plane, sigma y prime. So let's choose the easy way for the derivation. We replace theta with theta plus 90. So now we can write the sigma y prime equal to sigma half of sigma x plus sigma y minus because now you can see the cosine 2 theta, I wrote it here. If we replace with theta plus 90, then becomes cosine 2 theta plus 180, and then equal to negative cosine 2 theta. So we just change this negative sign to, sorry, positive sign to negative sign. So we have sigma x minus sigma y 2 cosine 2 theta. And for the last term, you replace theta with theta plus 90, so it becomes sine 2 theta plus 180 and is equal to negative sine 2 theta. So again, change the sign. Negative tau xy sine 2 theta. So we have, this is the third equation. Now we are done with sigma x prime, sigma y prime, tau x prime, y prime. So basically, any kind of rotation, as long as we know the theta, we can calculate the stress, plane stress after rotation. Any question? And now also, let's compare this equation and this equation. Something we can easily see is that if we add these two equations, sigma x prime plus sigma y prime equal to sigma x plus sigma y, and this term to cancel out, right? So we can see that from, if we add these two equations, one conclusion we can get is that no matter how we rotate our square for 2D, of course, or let's say if you go to more advanced class, well, no matter how we rotate our cube, the normal stress, the sum of normal stress does not change. Let's say for what we learned for now, for this mechanics material class, we know that after rotation, sigma x prime plus sigma y prime equal to sigma x plus sigma y. And of course, we can use this conclusion in your homework, in your quiz, in your exam. So basically, let's say you use the first expression to calculate sigma x prime. And actually, you do not need to use this equation to calculate sigma y prime. It can easily be calculated if you know the sigma x, sigma y minus sigma x prime, it should be equal to sigma y prime, right? But of course, you can use this one to calculate sigma x prime, you can use this one to calculate sigma y prime, and in the exam, you want to make sure that your calculation is correct. So you can just use double check the sum of sigma x, sigma y, and after rotation, sigma x prime, sigma y prime, they should be the same. So let's write this one here. And this is the same after we expand to the 3D situation. So let's say in the 3D situation, we have the sigma a, sigma x, sigma y, sigma z. And after rotation for the cube, we have the sigma x prime, sigma y prime, sigma z prime. Normally, we would use the eigenvalue of 3x3 matrix to calculate that in more advanced class, but it keeps the same, conclusion is same. The sum of this normal stress should be maintained the same. Or I can write it as sum of normal stresses it's just in general for 3D situation on a cubic element. Is independent of the orientation of that element. And of course, before we start our example problem, one thing I want to make it clear is that the sign convention of a stress component, because we know that, let's say, for this 80, 50, when you plug into the equation, we already have the equation we can use directly. When we plug into equation, we need to know that, well, should this 80, we should use negative or positive, this 50, should we use negative or positive? Of course, tension compression should be simple because you know that every time like when you see a compression, so obviously this one should be a negative value when you plug into the equation because this is a compressive, right? Stress. And when you plug this one into the equation, of course, you know that this is a tensile stress, so you need to use positive. And the thing get more complicated is shear. I mean, if it's shear in this direction, in this direction, in this direction, in this direction, should we put like positive value, positive 25 or negative 25 in the equation? So I think it's necessary to make the sign convention very clear um, for this topic. And later on, like I can draw this on this element, I can really put any different number I want, any direction I want. Um, the process should be the same as long as you understand basics. So let's talk about sign convention of the stress components. So the stress components, I think I mentioned before, they are the second order tensor and the sign convention follows the second order tensor. So let's say, for example, let's for plane stress situation, let's draw a square here. And of course, normally we would define from left to right as the x-axis and upward as y-axis. So let's say, even though most of the time we use sigma x, sigma y, sigma z or something, but second tensor we normally have two subscripts. Let's use sigma xx, sigma yy here. In some textbook, you will see that sigma xx, sigma yy, sigma zz, and some textbooks they use sigma x, sigma y, sigma, because normal stress is always on that plane in that direction. So, but here, since I want to explain the sign convention, I think it's necessary to put it back as sigma xx, sigma yy. And let's put this one as tau xy. And of course, if that is the direction on the x plane, this should be the direction of shear stress on the y plane, since this element should be in equilibrium. And of course, on the other two sides, on the bottom surface, we should have, this is also sigma yy, and this is also, this is a sigma xx, and of course, this is tau xy, and this is tau xy. So I also explained in the chapter 1 that the first subscript is always represent the plane. So let's say this sigma xx means, even though most of the time we use sigma x, so this sigma xx means it is on the x plane. This is x plane, right? And in the x direction, let's put the coordinate here. So a lot of time you will not see the coordinate, but by default, you would consider if it's not given, left to right is positive x, upward is positive y. If the coordinate system is not given, and then you use right hand rule, you know what is z direction. So now let's say this plane is facing the positive x direction, so this is the positive x plane, and it's in the positive x direction. So this not sigma x, it means on the x plane in the x direction, and the same thing, y plane y direction, and tau xy means on the x plane in the y direction. And for the sign of the stress component, as I said, since it's the second tensor, let's say first subscript explains, second subscript is the direction. If it's on the positive plane in the positive direction, the stress should be positive. So let's say for this component is positive plane, positive direction, so this stress should be positive. And you guys may ask, how about this one? This is also sigma axis. So for this one, as you can see here, the plane is facing the negative x direction, and the direction is also in the negative x direction. So it's negative, negative, it's still positive, right? So this is a good example. This is also sigma axis. And now the first subscript represents the plane. This is a negative x plane because it's facing the negative x direction. And also the stress is pointing towards the negative x direction. So plane is negative, direction is negative, and this one, the stress should be positive. And the same thing if you want to check sigma yy, here it's the positive y direction, the surface is positive, and it's also directed towards positive y direction. So again, positive, positive, positive. And you can also say that this is also sigma yy. And of course, this is a negative y plane and point toward the negative y direction. So negative, negative, positive. So this is the sign convention for second order tensor. And how about let's say if we have I just added here, if we have something like this, sigma axis. So basically mean that if we have this one, so this becomes on the positive x plane, but pointing towards the negative x direction. So now these stress components, if point in this direction, it should be a negative sign for the stress. So basically, if we have on the positive plane in the negative direction, should be negative. And similarly, let's say if we have a stress component like this. So now this one becomes on the negative plane. This surface is facing towards negative x direction, and this blue stress component sigma xx is pointing toward positive x direction. So it becomes the plane is negative and the stress is pointing toward positive direction, so the stress component is negative. So as you can see here, this is a sign convention for stress component, and also you can easily understand this is a sign convention for second order tensor because stress component is a second order tensor. And of course, this does not contradict with what we learned before. As you can see here, we analyze these two, we get a positive stress component, and we also said before, anything that is in tensile, no matter its stress component, internal force, elongation, strain, internal force, they all should be positive. So of course you can use this sign convention to determine the positive and negative sign, or you can just easily use these two will generate tensile stress. That's why these two are positive. If we are consider this red and blue, these two, you can use second order tensor this sign convention to get a conclusion that it's negative stress component, or you can simply consider because if we have the red and blue stress act on this element, it will generate compressive stress. So that's why it's negative. So for tensile for normal stress, I think it's kind of easy. You probably don't need this one to determine its positive or negative sign when you plug into the equation. You can easily consider does it generate tensile or does it generate compressive, right? The thing is that when it comes to the shear stress, you do need this one to determine if the shear stress component is positive or negative. So let's use this one for example. This is on the positive x plane. The surface is facing the positive x direction, and it is in the positive y direction. So it becomes positive plane, positive direction, stress component should be positive. Same thing, this one. This is also on the positive y plane and in the positive x direction, right? This is positive y plane, this is the positive x direction. So same thing. We can also choose this one to check. So let's say for this one, this is also well, this is tau x, tau x1, tau x, the magnitude should be the same. For the sign convention, let's check. This is on the negative y plane and it's in the negative x direction. So negative should be positive, right? And now let's check this component is on the negative x plane in the negative y direction. Negative, positive. So if we have a shear stress in this way, in this coordinate system, this stress component is positive. But of course, what if we have a stress component like this? So, and of course, this is still tau x plane in the y direction, but now it's still positive x plane, but it's negative y direction. So now it becomes positive plane, negative direction should be negative. The sign for the stress component should be negative. So again, for normal stress, we probably do not need this one to determine sign convention because we can simply use the tensile compressive to decide. Shear stress, we do need this sign convention. So just be careful, like when you see a number on a square element for plane stress situation, when you see the arrow in some direction, you need to know what is the actually value you need to plug into the equation. Sometimes the positive, sometimes negative. You need to decide based on sign convention. Any question?
Yes, sorry. How can you tell if the plane is positive and negative?
For any plane that is facing the positive direction, they are positive plane. So basically for this one, this plane is facing the positive x direction. So this is the positive plane. And this plane, well, you do not consider this is like a, I draw the line here, but you consider this is a square. So let's say this is a wood square you take out from the beam. This is inside, right? It has the wood inside. So now for this square, this surface is facing the positive x direction. This is a positive x plane. This surface is facing the negative x direction. It's the negative x plane. Make sense or not? And again, this one, this surface is facing the positive y direction. So it's positive y plane. And this surface is facing the negative y direction based on coordinate system. So this is negative y plane. And of course, I think it's better that you just imagine this is not like empty part. Otherwise, you don't really know what the plane means. You just consider this is a aluminum plate. When you consider the fuselage as a plane stress situation, you take a small square out of the fuselage skin, and you are doing analysis of the data stress analysis for that small element you take out from here. Make sense or not? Yeah.
Yes, thank you.
I have a
So-
question.
Yeah.
Sorry. You said the last shear stress, you said it was negative. I was questioning how it was negative because if it's pointing in the it's pointing in the negative direction and it has a negative component, but it's in the positive plane, wouldn't that make it back to being positive? Wouldn't the sign convention make it go back to being positive?
If it's on the positive x plane,
Yes.
X-plane in the negative y direction,
Yes. And it has a negative component.
Yes,
Would that, is the sign convention positive or negative? Because I thought you said it was positive, or maybe I misheard you.
that said it's positive. No, I said it's negative.
I was questioning how is it negative? How
So
about we
this one, let's make it clear again. If for this component, it's on the positive x plane in the positive y direction. So this stress component is positive. For this red arrow, this one is on the positive plane, but it's in the negative y direction. Positive plane, negative y direction. So this stress component is negative.
Oh, okay. Oh, okay, I see.
Yeah. Or I can do one more. Let's say if we have this blue one. Now, this shear stress component, it is on the negative y plane, but it's pointing towards positive x direction. So this component, this blue arrow point, this shear stress component, if we have this stress component, it should also be negative stress. Negative,
Okay.
negative shear stress.
I see. I understand now.
Okay.
Thank
Any
you.
other question? You're welcome. Any other question?
Sorry, yeah, I just want to clarify kind of on top of that. I understand all of that convention, but I'm
Yeah.
just trying to understand how, like, you know how regularly with our shear force, I know this is stress, but for our shear force sign convention, like V going down would be positive. Sorry, I might have not heard if you mentioned that, but
Thank you for the great question. I will think about should I talk about that or should I not talk about that? That's a really great question, great observation. Yes, you are correct. So remember that we talked about the sign convention of internal shear force. We said this one is positive, right? Remember in the first class of this semester. You are correct. And now, because the second law tensor, now this becomes positive. So here's the thing. I used to talk about it in the class, but I try not to put in the class anymore because it causes a lot of confusion for the students. But the true thing is that in the statics, there's no confusion. We always consider this is a shear force, and in the statics, that's really not mentioned the stress component or anything. So everything was okay. In the FEA, aerospace structure, Mach 1, or any kind of more advanced class than mechanics materials, there was no confusion because we always use this sign convention for stress component. But the problem is when I teach mechanics materials, there's a conflict. So what happened is that for the group of people who are in the statics and in the mechanics materials, when the stress component is not involved, they have originally a set of sign convention that always consider this is a positive shear force. They are very consistent. And now we have a new group of new generation of people who are working on the stress component, who are working on the FEA, who are working on like all different advanced kind of solid mechanics. They decide to use second law tensor for the stress components. And if you can check all the high level class, there's no conflict. The only thing that have some conflict is in mechanical material because we kind of mention the shear force sign convention from statics. We kind of trying to connect with something you need to use in the future classes. So yes, you are correct. But I don't want to really confuse you guys. Yes, there's a conflict of the sign convention. And also, I do believe the sign convention of stress component and the sign convention of the internal shear force should be the same. Because if you just imagine that internal shear force should be integration of shear stress on that area. Make sense or not? The internal shear force should always be the integration of shear stress on that area. Same thing for normal stress. The integration of normal stress on the area should be the internal normal force. Right? that one does not have any conflict because I can say that, okay, this is a positive internal normal force. This is also positive internal normal stress. There's nothing like complete things here. The thing is that we do have a conflict information here. So everything from the statics, from the first series chapter mechanics materials up until the shear force diagram, bending moment diagram, everything we still follow that kind of convention. Yes, we consider this a positive shear. Once we start to having the stress component, this is also convenient for your future study because if you go to the aerospace structure, if you go to the FEA class, if you go to Mech 1, everyone is like consistently use this sign convention. So you just consider well.
So just everything now on to this point, we're gonna use this, and then beforehand we kind of use the sign convention
Yes.
for.
Yes.
Thank
or
you.
Let's we can say that because in your exam 3, I do expect that you know shear force diagram, bending moment diagram, you know the stress component. So let's say in this way, everything for the content up until the shear force diagram and bending moment diagram, we use the previous sign convention because that is a type of sign convention generated by the group of people who were really working the statics and the mechanics materials. But for anything related to stress components and the sign convention for stress components, we use this one. And in the more advanced class, this is the only one. In the more advanced class, no one will say, okay, this is a positive shear or something. No. So
So this
great.
is like the transition.
Yeah.
Okay.
Yeah.
Thank you.
You're welcome. Any other question? Okay, so now we are clear about these 3 equation. We are clear about the sign convention. Let's check the example problem. Let's see how to put these numbers into our equation to calculate the new status stress on the inclined plane or after rotation. So static plane stress is given here, and of course, when the coordinate system is not given, you always use this one as a coordinate system. This is always left, right, positive x, upward, positive y. Determine the static stress at a point on another element oriented 30-degree clockwise from the position shown. So, and of course, we have the equation already. Let's move the 3 equation here. Let's move the first one. Of course, there's nothing tricky here. You just plug number into the equation. But first, let's make it clear what numbers are each of, let's say for sigma x. Should we put positive 80 and negative 80? It's given at 80 in the graph. Should we put positive 80, negative 80? Yes, negative 80. Sigma y? Sigma y? Positive, thank you. Tau xy? Positive 25, negative 25. Negative, thank you. Let's explain one more time. This component is on the positive x plane in the negative y direction. Positive, negative should be negative. And of course, I forgot to put the unit, so it's megapascal. Well, I'll put it later. And also to plug into the equation, we also need to know the theta. What is theta? What is the theta? Anyone? 30. Negative 30. Let's do a vote. Positive, negative. Well, let me, whenever there's like confusion, always go back to the basic concept. I think I emphasized in last class that before I did our derivation, our whole derivation is based on the definition that theta is from the global x counterclockwise to x prime. So now if you have a square that is rotating clockwise 30 degree, then it should be negative 30 degree. Or of course you can do 330, right? That is also correct. So be very clear that all our derivation are based on this angle is counterclockwise. But of course, you can derive your own set equation based on clockwise. Then you cannot use the equation with deriving class. But if you want to use the equation with deriving class, always remember that theta should be counterclockwise. So let's put negative 30 degree or 330. So the rest part, of course, is very simple. Just plug a number into the equation. Minus 50 and cosine negative 60. $25 sine negative 60 degree. This one is equal to megapascal. And for the tau x prime y prime, again, plug into the equation. If we need to use this equation, we'll be providing a quiz or exam, or we don't have any quiz anymore, but we'll provide an exam. Sine 2 theta. So we have 60 degrees because 2 theta. Theta equals to negative 30. Negative 80. Minus 50 sine negative 60 minus shear stress 25 cosine and of course, as I said, since the sum of the sigma x, sigma y, and sigma x prime, sigma y prime should always be the same. So you can use that one to calculate, but let's use the equation to calculate and then see if the match. Hi. What do you want? What do you want? The kitty name is Sweetie because she's super sweet. Can you have it? Um, you can come to my office hour and yeah, and communicate with her one by one with my cat. Have -80 minus 50 cosine -60 plus 25 sine. So this is -4.2 megapascal. And you can see that this one plus this one equal to -30 and sigma x plus sigma y equal to -30. So we are correct, right? Does your cat know how to solve the shear stress question? Of course, she's an expert. I teach her every day since she was 3 months old. So this is the stress component after rotation, or I can put it on a square to show you that. Let's say this is the square that is rotation for 30 degree. Wait, I feel like you guys have more interest to my cat than my lecture. I feel sad. You guys should focus on my lecture, not my cat. X prime negative, so clockwise 30 degree. So compression on X prime, 25.8. And sigma Y prime negative. So this is 4.2 megapascal. Tau X prime Y prime also negative. So this is the tau XY 68.8. And of course, if this is tau XY prime on the positive X plane, the out plane can be easy identifying this way because your cube cannot rotate or your square cannot rotate for 2D. Should be in equilibrium. Sweetie, come here. Come here. Come here. Well, she's busy. She doesn't want to teach this class. Sorry. So any question? Oh, this is some like extra I just added here, but I mean in your homework in your exam, you don't really need to put it. This just help you understand like what does mean after rotation for 30 degree clockwise. In your homework or in your exam, you just need to write this. So basically, when you have a correct sign, when you in your calculation and your final calculation, you have positive and negative sign. That positive and negative sign already represent very clearly what does it mean based on our sign convention. So you don't need to explain like, okay, this negative sign is compressive. This is if it's on x positive x prime plane, you should negative y. No, you do not explain. As long as you calculate this correct number, everything is fine. When we say a negative sign for normal stress, we know it's compression. When we say a positive sign for normal stress, we know it's tension. There's no further explanation needed. And you don't need this one in your homework exam. This I just draw here to help you understand what does it mean after rotation for 30 degree.
I have a question.
Yeah.
Oh, so if we had like a z-axis, if this was three-dimensional, it would just be the same, like same concept, but just with an added axis, with an extra degree of with another degree,
Sorry.
another axis.
Sorry. Well, could you please repeat the question?
I was saying if we rotated this in the third dimension with a z-axis, it would be like the same concept with this another axis of rotation.
Yes, yes. So basically it's either a I don't have this is a 2D problem. Now if you have a 3D problem, then your cube can rotate in a 3D space. If it's 2D problem, it's only rotated in, let's say, XY plane, right? So this is like rotating XY plane. But if you have a cube and your cube can rotate in 3D space, so all three direction. So yes, it's the same concept. But for 3D problem, we are only teaching the Mach 1 and aerospace structure. Yes. Is it clear?
Yes.
Any other question? Okay, so if no question, let's move on to a new topic. So of course, this is a rotation for any random degree. For theta degree, it can be any value, any degree from 0 to 360, of course. But as our engineer, we want to know that in what orientation your normal stress reached the maximum. Let's say if we have a brittle material, because as I mentioned, brittle material break because of normal stress, right? It's breaking between the bond between of the atoms. So for brittle material, we want to know at what angle rotation that the normal stress would reach the maximum. So that is our main concern. And we know that if this structure would fail, it will fail in that inclined plane, which is, I can use this one to explain later, like why it fail in certain plane. And also for some material, let's say if for most our structure engineers, we use the metal, right? So it's ductile material, well, majority metal. Let's say aluminum, we use on aircraft structure, they are the ductile material, and we want to know at what orientation or on what plane the shear stress reached the maximum. So we know that that plane probably is the most dangerous plane, or it highly likely will fail on that plane. So let's say we already have a general equation for deriving the sigma x prime, sigma y prime, tau x y prime after rotation any angle theta. Now we want to find the extreme value, sigma x maximum, and of course, when one reached maximum, one reached minimum for the normal stress, and also tau xy maximum. So how should we do that? How to find the extreme value if we already derived the equation sigma x prime, sigma y prime as function of theta, and tau xy prime, y prime as function of theta? Mathematically, first derivative equal to 0, right? Yes, yes. So we already have the expression here. So basically, let's say if this sigma x prime is a function of theta, and theta can be any value, and if you want to know at what theta angle this sigma x prime reach maximum, we just need to mathematically take this one with d theta x prime d theta when this one equal to 0. That is the orientation that the normal stress reached maximum. Same thing, if it's ductile material, if we have the d tau d theta equal to 0, and that is the orientation that of the element of the square that shear stress reaching maximum, and then we know that shear stress, ductile material will fail on that plane. So this is the idea of the principal stress and the maximum shear stress. It's in chapter 7.1b. So principal stress means the normal stress reach maximum. And of course, if one normal stress, let's say if I rotate I don't have a square, but let's say this is a square element in xy plane. This is global x direction, this is global y direction. And I rotate a plane that if one plane, let's say if one plane, the normal stress reach maximum is automatically the other plane reached minimum. So we have, there's a definition of the principal stresses. Normal stress reach maximum and minimum, no shear stress. Shear stress disappeared. No shear stress. And mathematically, we just take the derivative. Let's just copy and paste to save some time. Wait, I think I have this. Okay, yeah, it's this equation. Let's say for this equation we derived, we use d sigma x prime d theta. And of course, this first component is wrong. The first component is gone because because this one there's no theta here. In terms of function theta, this one is constant. So start from the second term. We have negative, just negative. After take a derivative of the cosine theta, sigma x minus sigma y, and sine 2 theta. To save some time, you can check or just Google it, like how to calculate derivative of cosine 2 theta. So basically is there's a negative sign, and also because there's a 2 here, so you take a derivative, there's also 2 come out. This is not the content of mechanics materials, but just like basic math. And also this one first derivative, we have 2 tau xy cosine 2 theta. This one should be equal to 0. So, and of course, when it sets this one equal to 0, sine theta, cosine theta, we get tan theta. Two theta equal to 2 tau xy theta x, sigma x minus sigma y. And we consider this is when the rotation, wait. No. I'm confused. Sorry. Let me do again. Okay, it's back. Sorry about that. So since this is solved when the first derivative equal to 0, so it's the orientation of the element when it's principal stress. So I add the p here as subscript. So it's the rotation of when it reach the principal stresses. That's why we have p here. So solving this one, we have sigma 1. Actually, we use this to solve for theta p, and we have 2 roots when we solve for theta p, and they are 90 degrees apart, of course. And we plug the theta p back into the equation, we get a theta 1 and theta 2, which are the principal stress. Theta p1 and theta p2. And they're 90 degrees apart because it's tangent. You can Google check what is the tangent curve look like, and you can understand why it's 90 degrees apart. And so we have the principal stresses equal to principal stress. We normally use sigma 1, sigma 2 for 2D situation. If it's a 3D situation, we use sigma 1, sigma 2, sigma 3 for the 3 principal stresses. And we have a convention that sigma 1 is greater than sigma 2, greater than sigma 3. And for our 2D situation, plane stress situation, of course, is sigma 1 greater than sigma 2. So you have 2 principal stresses. The larger one we define as sigma 1. Smaller one we define as sigma 2. Plus or minus square root of sigma x minus sigma y squared plus tau xy squared. And of course, plus becomes sigma 1. If you minus a positive term, it's smaller number, it's sigma 2. So let's put the convention here. Normally, it's sigma 1 is the maximum principal stresses, and sigma 2 is the minimum principal stresses. But of course, this is for plane stress situation. If for 3D, it's sigma 1, sigma 2, sigma 3. So sigma 1 is the maximum, sigma 3 is the minimum. And in this situation, shear stress disappear, equal to 0. Or you can just mathematically plug the theta p into the tau x y prime equation, you will get 0 value. So this is a, wait. I put the wrong graph here. I put the wrong graph here. I'll do it again. I'll put the correct graph back in the next class. So this is the principal stresses derivation. It's the basic idea is very simple. It's just pure take the first derivative with respect to theta equal to 0. We get the theta p, which is the orientation of this square element when the normal stress reaches extreme value. And we solve this theta p. And because the tangent curve, it's like 90 degree apart for each tangent curve. So for the two roots, they're 90 degree apart. You can Google check all this like basic math thing. So now you plug the theta p back into the equation. Of course, you get the actual extreme value of the sigma. So for the convention, we define the larger one as the sigma 1, the smaller one as sigma 2. So, and of course, you can see from the equation, if you use plus, it's the sigma 1. If you use minimum, sorry, you use negative, minus this positive value, it becomes the minimum and sigma 2. So this is how we find the principal stresses. And of course, you plug this theta p into the shear stress equation, you get 0. So this is the derivation part for finding the maximum normal stress if the material we use for our structure is a brittle material. This information is very important because we can use this equation to calculate what is the orientation of the maximum normal stress and what is the value of the maximum normal stress. We can compare this value, maximum normal stress in your structure with the strength of the material. And you know it will fail or not. If it fail on which plane? Right, make sense? Now, let's say, what if we use material that is ductile material? Then we need to figure out when the shear stress becomes maximum. And we know that on that plane, well, it will fail. And again, we are comparing the maximum shear stress in the structure with allowable shear stress of the material. So this derivation part is just saying, we take the first derivative of the tau x prime y prime with respect to theta, we get 0 value, we get an extreme value. So for maximum shear stress, first derivative equal to 0. So we have the equation derived already, so I will write it here, tangent to theta. I use subscript S represent the maximum shear stress, and it's equal to negative sigma x minus sigma y, and 2 tau xy. So this is the theta when the shear stress reached the maximum. And now if we compare these two, this is a theta when the normal stress reached the maximum and minimum, which reach extreme values. This is the shear stress reached the maximum. And you can see that this one times this one equal to -1. What does it mean? Like 2 tangent value equal to -1. It means these two angles, they are 45 degrees apart, right? Again, Google check all this basic math. We don't have a lot of time to explain the like tangent, sine, cosine, derivative, and kind of thing. So when we compare these two equations, we know that the tangent to theta s times tangent to theta p equal to -1. So we have theta s, theta p, they are 45 degrees apart. And this is a very important information, which can explain why we had, like, why sometimes it fails on a 45-degree plane. Sometimes it fails on this like 90 degree to the actual direction, or sometimes it fails because on this 45-degree plane. We don't have a lot of time to explain in this class, but I will try to explain in more detail in the next class. Let's finish this derivation part. So again, we want to know the maximum shear stress value. So tau max equal to, if you plug the theta s into the tau x prime y prime equation, you get sigma x minus sigma y squared plus tau xy squared. And of course, all this equation you can use directly in your homework, in your exam. Let's also put this one clear. So this one means that theta s, theta p mean that the normal maximum shear stress is 45 degrees to the principal stresses. It's 45 any direction. No, it's basically, well, you can use this one to solve a theta s, and you plug into the equation, you get the maximum, but it's not really like any direction. It's, let's say if you solve the principal stress direction first, I'm multiplying these two just to show you that actually if you compare the direction of the maximum normal stress and maximum shear stress, they are 45 degree apart. So let's say if you solve for the normal stress, the maximum normal stress, that is at a certain orientation, let's say at this orientation that you have the normal stress reach extreme value and all the shear stress disappear, and the maximum shear stress should be 45 degrees. Let's say this is a X prime. Then it should be maximum shear stress should be 45 degree to this X prime direction. It's not 45 degree in any direction. It's 45 degree to the principal stress. Any other question? And of course, if you plug in this theta back to average, because when the normal stress reach maximum, shear stress is disappear. But when shear stress reach maximum, normal stress does not disappear. When you plug into the equation, you have the average shear normal stress becomes well, let's remove this substrate. The normal stress at this orientation, when shear stress reach maximum, it becomes sigma x plus sigma y, half of sigma x plus sigma y. And sometimes the textbook use the sigma average, subscript average, but let's make it not that confusing. Basically, you solve for the theta s, you plug into the tau x prime y prime equation, you get the maximum shear stress. You plug in the sigma x equation, you get the normal stress at this orientation. Any question? We'll do the example in the next class. Any question for this part?
Really quick. So it's normal stress when the shear stress is maximum, you're saying?
Yes, yes, yes.
I had a question.
Wow, that's smart cat. Yeah,
So go back to the principal stresses.
Yeah.
So let's say we find theta p. If we plug theta p back into the sigma x prime formula, that
Yeah.
would give us the maximum. That would give us this formula basically. So this is like a shorthand version for if we plugged in theta p into
yes,
the equation. Okay.
yes. Yes.
Thank you. I was just wondering whether or not if I plug that back in, would I get the same answer? Thank you.
You can try after class, like plug in and see if you get this one. Any other question? If you guys want to see my cat, you can come to my office hour. Thank you for coming to my class today, and I will change the Zoom link to the office hour Zoom link. And have a great day. Thank you. Thank you.